Whoa, didn't see you there. I was just talking to my old friend Buffers here. I'm ready to do some fun stuff today. Why don't you come and watch with me? Now, you may be wondering, what is a buffered solution? Well, it's a solution that resists a change in pH when either hydroxide ions or protons are added to the solution. From this, we can infer that it is most likely an acid or a base reaction kind of dealing thing. It has something to do with these. So, what are some common examples? Blood. That's always something that we need to buffer in because our blood must maintain a pH of 7.35 in order for us to live, or else our blood becomes too acidic or basic, and then we die because no one needs that. And also, water is commonly a pH in rivers and lakes and oceans and whatnot because if the water does not maintain a certain pH, the fish will die from its acidity or basicity. I don't know what the word for that is. Basicness. So yeah, buffered solutions keep a solution in a certain pH range is the final way to say it. Components of a buffered solution include a weak acid and a conjugate base to go along with it, and water. Usually the acid is a salt, with the common reaction HA plus A minus yields A minus plus HA. This is because a weak acid does not usually dissociate in water, which means that the hydrogen proton on the acid will not come off. And also, the conjugate base will not dissociate in water because it will not remove a proton from the water molecule, H2O, because it is weak. Um, this being said, they remain in high concentrations in the solution. So, in a minute, I'll explain how they keep the pH from rising or lowering due to a increase in protons or hydroxide ions. Problem time. Yeah. Alright, so we're going to start off with a problem that has 0.5 molar acetic acid and zero point 0.5 molar sodium acetate, and we're going to calculate the pH of this buffered solution. So, to start off with, we'll determine the major species, which are the weak acid, acetic acid, sodium, which is neither an acid nor a base, uh, acetate, which is the conjugate base of the acetic acid, and water, which is a very weak base or acid. It always sways. And with further examination, it shows that the acetic acid will control the equilibrium of this buffer, and that's because the dissociation controls it. So the ice table for this reaction will look like this, with the acetic acid dissociating into the hydrogen ion and the acetate over here, with the initial concentration being 0.5 molar and then 0 on the H plus because it hasn't dissociated yet, and 0.5 molar on the acetate because it's already in the sodium acetate. And so then you can find the equilibrium constant, Ka, which in this case equals 1.8 times 10 to the negative fifth, which is the constant for acetic acid anyways. But in this case, we're trying to find the pH of the buffer solution. So we can do 1.8 equals H plus, the concentration of H plus, times acetate, the concentration, over the concentration of acetic acid. So that'll equal X times 0.5 plus X over 0.5 minus X, because that's the initial concentrations and the unknowns. But the 5% rule will apply to this. And alright, it's a new day, new shirt. Camera died last night. Either way, 5% rule still applies. That means that it's x times 0.50 over 0.50 is the abbreviated way of writing it. So you can get rid of the plus x and minus x on the top and bottom just to make the problem easier. By doing some math, you can divide out both of the 0.50s. This means that x is the concentration of the H+, and the pH of a solution is the negative log of the concentration of the hydrogen ions. In this case, x is 1.84 or 1.8 times 10 to the negative fifth, and the negative log of that is 4.74, which is the pH. So yeah, that's how to determine the pH of the first buffered solution. So that's just the easiest way of doing this. It's the easiest type of problem. Here's another harder problem that we'll go over. Alright, before we get to the hard stuff, let's talk about what the dissociation equation for the hydrogen ion is. So it equals Ka times the concentration of the acid over the concentration of the base. This is commonly used for determining the hydrogen concentration in a buffered solution. Another way of putting that equation is pH equals pKa, which is the negative log of Ka, just like pH is the negative log of the concentration of the hydrogen ions, plus the log of the base over the acid. Now this is really useful because it can determine the pH of a buffered solution when the ratio of acid to base is known. This is called the Henderson-Hasselbalch equation. It is probably the most commonly used equation in buffered solution calculations just because it is so simple to use if you know the ratio. Now it can't also always be used because you don't always know the concentrations of each variable, but in this case we do know it. So this is just an easier way to determine the pH of a buffered solution. Alright, time for something harder. We're going to try to figure out the amount in grams of sodium acetate that we need to add to 0.5 liters of acetic acid at 0.2 molar to create a buffer solution with a pH of 5.0. I'm just going to do a little speedy montage and then I'll explain it afterwards what I've done. Alright, to start off with, we determined the concentration of the acetate in this solution. I'll get to the determining the grams in just a second, but this is the part that we just learned kind of section. So, using our Henderson-Hasselbalch equation, we can set up pH equals pKa plus the log of the acetate over the acid, the acetic acid. So we know that the pH was 5. So, we don't quite know the pKa yet, but we can find that. And this also equals the log of the acetate minus the log of the acetic acid. The pH does. So if we look in the back of the book, we can find the Ka value for the acetic acid. Now to find the pKa value, we take the negative log of the Ka value, which in this case was 1.8 times 10 to the negative fifth, what we've used in previous problems. And we find that it is 4.75 when it's rounded off. So we can do 5 equals 4.75 plus the log of acetate minus the log of the concentration of the acetic acid. And then by doing so, we can also find what the concentration of the acetate is, because we know that the concentration of the acetic acid is 0.2. So the log of the acetic acid, 0.2 equals negative 0.7. 5 minus 4.75 equals 0.25, so we can eliminate that step, which in turn equals the log of the acetate minus negative 0.70. If we add 0.70 to 0.25, we get negative 0.45, which then equals the log of the acetate, because we've canceled everything else out. Then we take the negative log of the negative 4.5, negative 0.45, and that equals 0.335 molar, which equals the concentration of the acetate. So now I'm going to do how to determine the grams based off of the molarity of the acetate. Alright, to figure out the moles of NaC2H3O2, or sodium acetate, needed, or rather, just acetate, because the sodium is irrelevant in creating the buffer, we can use our calculated concentration, 0.335 moles per liter, times the liters of the acetic acid in the solution, which is 0.5 in this case. And by multiplying those, we get 0.178 moles of NaC2H3O2 needed, which also means that 0.178 moles of acetate are needed, which is what we're looking for. The molar mass of sodium acetate is 82.03 grams per mole. And when we take moles times molar mass, we get 14.56 grams, and when we round it, we get 15 grams of acetate required to make this buffer at the pH of 5. So that's how you do it, kind of combining all of the things that we've talked about. And now we'll move on to something sort of more exciting called buffer capacity. Alright, something fun. Buffer capacity. Well, it's kind of what it sounds like it is. So, buffer is made up of weak acid and its conjugate base. Well, it can hold off the OH or protons being thrown at it for a certain amount of time to keep the pH the same, but it will eventually break. It's a weak acid. It's not that strong. And the amount that of OH or the protons from a hydrogen that it can absorb is called the buffer capacity. Now, a buffer solution with high concentrations of a weak acid and its conjugate base will absorb more OH or protons than one with a lower concentration. So, the one in a higher concentration will have the larger buffer capacity. That's the kind of idea behind a buffer capacity. Problem time! Alright, let's do a problem. Let's determine the change in pH when 0.010 moles of HCl in the gaseous state is added to 1 liter of 5 molar acetic acid and 5 molar sodium acetate. And the Ka of acetate is 1.8 times 10 to the negative fifth. So, there we go. Actually, that's the Ka of the dissociation of the acetic acid. That's already been through. Okay. Cue the montage. Alright, so let's talk about this and see how I did it. To find the initial pH of the solution, we can take the negative log of 1.8 times 10 to the negative fifth, which equals 4.74, and in this case, the pH and the pKa. Alright, so we have an ice table here, right here. Yeah. That's got our net ionic reaction, H plus acetate equals acetic acid. We start off with the initial concentrations, 0.01 molar, 5 molar, and 5 molar. Then we've got minus X, 5.0 minus X, and 5.0 plus X. So we get our final values of 0, 4.99, and 5.01 molar. Then using the Henderson-Hasselbalch equation, we can determine the pH, saying that pH equals the pKa, 4.74, plus the log of the base over the acid, the final concentrations, which is 4.99 over 5.01. And from that, we can do some adding and subtracting and whatnot and find that the pH equals 4.74 minus 0.0017, which is the divided out ratio of that, equals 4.74. So really there's no change in the pH from this because so little was added to such high concentrations of it that the buffer just absorbed almost all of it. So yeah, that's kind of the basic idea on buffer capacity. It's not really that hard, not really that big of a concept, but kind of fun to think about. So yeah, that's buffer capacity. Alright, let's do a summary. We're almost done. What is a buffer? It is a solution that resists a change in pH through the use of a weak acid and its conjugate base that absorbs the OH minus or the H plus ions that come to it. So it creates water out of these two things so that the pH will not rise because water is usually neutral. The weak acid does not dissociate in water, and therefore the species remain in high concentrations, and it can absorb large amounts sometimes of the OH and the H plus. To determine the pH of a buffer solution, we'll use the Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of the base over the concentration of the acid. Pretty simple stuff. And then buffering capacity is how much buffer solution can absorb of the OH minus or the H plus to maintain its pH range. So anything in a higher concentration, the buffers in the higher concentrations will absorb more and the ones in the lower won't. But eventually, once enough is added, it will always change. So yeah, that's the basics on buffers. I hope you enjoyed. Hey. Okay, Drew, what's your opinions on buffers?
Buffers, they never cease to amaze me. Just the idea that an acid and a base would not yield 7 pH. It blew my mind the first time we did it. And my mom told me that her personal downfall on the AP exam was in fact buffers. So I'm just amazed and confused about the whole deal. It's a very rough subject for me.